welcome to Easy BTech channel. So in this module we will see what is hexadecimal number system and how to convert the given hexadecimal number to equivalent binary, and given binary number how to find the corresponding hexadecimal equivalent, and we will see other conversions also. So till now we have seen octal number system, binary number system, decimal number system. So for binary number system, the base or radix is 2. For octal number system, the base or radix is 8. And whereas hexadecimal number system, radix or base is 16. For hexadecimal number system, the base or radix are 16. So as we have said, the different number of elements that are present in any number system are 0 to r minus 1. So the minimum element here is 0 and the maximum element 16 minus 1, that is 15. But the different elements that are present in the hexadecimal number system are, so from 0, starting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have whatever 10 that will come after 9 we will represent with A, whereas B corresponds to 11, C corresponds to 12, D corresponds to 13, E corresponds to 14, whereas F corresponds to 15. So total we will have 16 elements in the hexadecimal number system. Minimum element is 0, the maximum element is 15, which we will represent with the alphabetical letter capital F. So after, what we have to remember is, after 9 whatever we will get 10, that we will represent with A, 11 we will represent B, 12 we will represent with C, 13 we will represent with D, 14 we will represent with E, and 15 we will represent with F. So whatever number that we have to represent only by using these 16 different elements. So this is also one way of representing binary number system in a compact way. So it is also one way of compact representation of a binary number, because if we take 16, if we express in terms of 2 power 16, we can express in terms of 2 power as 4. So that's why 4 binary digits we can represent with a single hexadecimal digit. So we can group 4 binary digits, so correspondingly we can represent with a single hexadecimal digit. So we'll see the hexadecimal numbers, what are the corresponding binary equivalent, 4-bit binary equivalent for them. So for 0 it is 0 0 0 0, for 1 it is 0 0 0 1, for 2 it is 0 0 1 0, for 3 0 0 1 1, 4 0 1 0 0, for 5 it is 0 1 0 1, for 6 it is 0 1 1 0, for 7 0 1 1 1, for 8 it is 1 0 0, for 9 1 0 0 1. A means 10, that we will represent with 1 0 1 0. B means 11, that we will represent with 1 0 1 1. C means 12, that will represent with 1 1 0 0. D means 13, that will represent with 1 1 0 1. E means 14, 1 1 1 0. 15 means F, 1 1 1. So these are the hexadecimal numbers 0 to F, and these are the corresponding binary equivalent. So each hexadecimal number we can represent with a corresponding 4-bit equivalent binary number, or the other way, each 4-bit binary number we can represent with a single hexadecimal number. So that is why hexadecimal number system is also a compact way of representing a given 4-bit binary number. Now next we will see how to represent the given hexadecimal number in terms of positional weights. So as we have seen earlier also, so the here it is having only the integer part. So this is called LSB, least significant bit, whereas the leftmost bit is called the MSB, most significant bit. LSB will have the least weight, whereas MSB will have the highest weight. So each in a positional number system we will have the weights of the power of r power k. So here the radix is 16. So we'll have the weight 16 power k. So for integer part we'll have positive weight. For fractional parts we'll have negative weight. So starting from LSB we'll have 16 power 0, 16 power 1, 16 power 2 and 16 power 3. So how to represent this in terms of positional weights? So 3, you multiply the corresponding bit with respect to weight. 3 into 16 power 3 plus A means 10 into 16 power 2 plus 9 into 16 power 1 plus F means 15 into 16 power 0. So each bit you multiply with the respective weight. So this example 2D 3.5 is having the fractional part also. So fractional part will have negative weight. So this will have a weight of 16 power minus 1. This will have a weight of 16 power 0. This will have a weight of 16 power 1. And this will have a weight of 16 power 2. Now how to represent this in terms of positional weights? So 2 into 16 power 2 plus D means it is 13. So 13 into 16 power 1 plus 3 into 16 power 0 plus 5 into 16 power minus 1. So fractional part will have negative weight. We'll see one more example. So this is also having the integer part as well as the fractional part. Fractional part will have negative weight 16 power minus 1, 16 power minus 2, and integer part we have to write positive weight 16 power 0, 16 power 1 and 16 power 2. Now multiply the respective digit with weights. So 4 into 16 power 2 plus 5 into 16 power 1 plus B means 11. So 11 into 16 power 0 plus 6 into 16 power minus 1 plus 7 into 16 power minus 2. So this is how we will represent the given hexadecimal number with the respect to positional weights, right? Next we will see how to find the hexadecimal equivalent of a given binary number. Binary number is given to us. We have to find the hexadecimal number. So it is similar to how we find the octal equivalent of a given binary number. So for the integer part we have to scan the number from right to left. But here the difference is we have to group 4 bits. Here we have to group 4 bits. In octal, while finding the octal equivalent of a given binary number, we have grouped 3 bits. But here we are grouping 4 bits. So that is the difference while finding the octal equivalent and the hexadecimal equivalent. So in hexadecimal equivalent, we have to group 4 bits and then we have to write the corresponding hexadecimal equivalent. So similarly for in fractional part, we have to scan the number from left to right. So here also we have to group 4 bits and then we have to write the corresponding hexadecimal digit. So it is similar to finding the octal equivalent of the given binary number, but here instead of grouping 3 bits in octal number system, we have to group 4 bits. So that is the only difference. Rest of the thing is same. So this also we will see with the help of an example so that it will be clearly understand. So this is the number, binary number that is given to us. So it is having only the integer part, no fractional part. So we have to scan the number from right to left, right to left, right to left, and we have to group 4 bits at a time. That is the difference here. We have to group 4 bits at a time. So total 12 bits, binary bits. So we have grouped into 3 groups. So 1, 0, 1, 1. So if this is the binary number, the corresponding hexadecimal equivalent for this is, it is 11. So that means it is B. It is B. So next one is 0, 1, 0, 0, 0, 1, 00. The corresponding hexadecimal equivalent is 4, whereas for 0, 0, 1, 1, the corresponding 4-bit, for this 4-bit binary number, the corresponding equivalent is 3. So for the given binary number, the corresponding hexadecimal equivalent is B43. So this is the corresponding hexadecimal equivalent of the given binary number, right? Next, we'll see one more example. So this is the given binary number. We have to find the hexadecimal equivalent. So we have to, from right to left, we have to scan the number. And we have to group 4 bits at a time. So here we have left with only 2 bits. So we have to append zeros at the leading end or at the left hand side. We have to append 2 zeros. So if we append 2 zeros, so it is 0, 0, 1, 0. The corresponding hexadecimal equivalent for this is 2. So next 1, 0, 1, 0. So the corresponding hexadecimal equivalent for 1, 0, 1, 0 means A. Next 0, 0, 0, 1. For 0, 0, 0, 1, the corresponding hexadecimal equivalent is 1. So for the given binary number, the corresponding hexadecimal equivalent is 2A1, 2A1. So this is the corresponding hexadecimal equivalent. So here what we have did, we left with 2 bits. So we have appended 2 zeros at the leading side or at the left hand side. Next, so here we are having only the fractional number. For fractional number, what we have to do, we have to scan the number from left to right. Whenever we are finding the octal equivalent or hexadecimal equivalent for the given binary number, if it is having the fractional part, we have to scan the number from left to right, 4 bits at a time, because here we are finding the hexadecimal equivalent. So we left with 3 bits, so we have to append one more 0. So 1 triple 0, this is the binary, this is the 4-bit, the corresponding hexadecimal equivalent is 8. Next 0, 1, 00, the corresponding hexadecimal equivalent is 4. So for the given binary number, the corresponding hexadecimal equivalent is 0.84. So we have to finding the hexadecimal equivalent. What we have to do? We have to scan the number from left to right. So whenever we have insufficient bits for the fractional part, we have to append zeros at the trailing and or at the rightmost part. Right? Then you will see one more example. So this is also having the integer part as well as fractional part. So integer part is having only 3 bits. So we will append 1 0 at the leading end. So this will become 0 1 0 1. So the corresponding hexadecimal equivalent for 0 1 0 1 is 5. Next, for fractional part, we will scan the number from left to right. So 0 1 0 1, and this here also we left with 3 bits. So here we will append 0 at the trailing end. So it is 0 1 0 1. Here also 1 0 1 0 1. So the corresponding hexadecimal equivalent is 5, and then we have triple 1 0. Triple 1 0 means it is D. Sorry, E. Triple 1 0 means it is E, right? So the corresponding hexadecimal equivalent for the given binary number is 5.5 E. 5.5 E. So this is the procedure we have to follow for finding the hexadecimal equivalent of a given binary number, right? Next, we will see how to find the binary equivalent for the given hexadecimal number. How to find the binary equivalent to the given hexadecimal number. This is also similar to octal to binary conversion. So we have to just write for each digit, each hexadecimal digit, we have to write the corresponding 4-bit binary equivalent. So what is the binary equivalent for 3? It is 0 0 1 1. So this is the corresponding 4-bit binary equivalent for the given hexadecimal digit 3. Next, A means what is the corresponding hexadecimal digit? It is 1 0 1 0. So this is the corresponding binary equivalent for the given hexadecimal digit A. Next, 5 we have. For 5 the corresponding binary equivalent is 0 1 0 1 0 1 0 1. Now we have to write the corresponding binary equivalent in the same order. 3 means 0 0 1 1. A means 1 0 1 0. 5 means 0 1 0 1. So this is the corresponding binary equivalent for the given hexadecimal number 3A5. For the given hexadecimal number 3A5. So this is the corresponding binary equivalent, right? Next we will see one more example. So here we are having the integer part as well as fractional part. So it doesn't matter if we have integer and fractional part. Only the procedure that we have to follow is we have to write the for each hexadecimal digit the corresponding 4-bit binary equivalent. So 1 means the corresponding binary equivalent 0 0 0 1 0 0 0 1, and 2 means 0 0 1 0. 3 means 0 0 1 1 0 0 1 1. D means it is 13. 30 means 1 1 0 1 1 1 0 1. So the corresponding binary equivalent for the given hexadecimal number 12.3D is 0 0 0 1 0 0 1 0. So this is for the integer part. For fractional part it is 0 0 1 1, and for D it is 1 1 0 1. So this is the binary equivalent of the given hexadecimal number 12.3D, right? So we have to write in the same order. If we interchange the order, the equivalent is not correct. We'll see one more example. So 1.8, the given hexadecimal number is 1.8. How to find the binary equivalent? For 1, it is 0 0 0 1 0 0 0 1, right? And for 8, it is 1 triple 0 1 triple 0. So it is simple and straightforward. So for the given hexadecimal number 1.8, the corresponding binary equivalent is 0 0 0 1.1 triple 0. So this is the corresponding binary equivalent for the given hexadecimal number, right? So next, another important thing is how to convert a given hexadecimal number to octal equivalent, or how to find the octal equivalent of a given hexadecimal number. Till now we have seen, we have find binary equivalent for the given hexadecimal number, or octal equivalent, or for the given octal number we have find binary equivalent. Now we will see how to convert the given hexadecimal number into corresponding octal equivalent. It is also very simple and straightforward. Whatever we have seen till now, those only we will apply here. So first step is the given hexadecimal number, we will convert it into, we will find the binary equivalent for this hexadecimal number, and from that we will convert the binary into octal number. So first we will convert the hexadecimal number to binary, and then we will convert from binary to octal. So that is the procedure that we have to follow while finding the octal equivalent of a hexadecimal number, right? So we'll see with the help of this example. So for 3, the corresponding binary equivalent is 0, 0, 1, 1, 0, 0, 1, 1. For B means it is 11. So 1, 0, 1, 1, right? Next 4 means it is 0, 1, 0. So first we will find the binary equivalent for this. So what is the binary equivalent? 0, 0, 1, 1, 1, 0, 1, 1, and then 0, 1, 0. So this is the binary equivalent. This is the binary equivalent. Now we will find the octal equivalent. So what is the procedure that we need to follow now? We will scan the number from right to left, or from LSB to MSB, and we will group 3 bits at a time, and then we will write the corresponding octal equivalent for the given 3-bit binary number, right? For the given. So first we have written the binary equivalent for each of hexadecimal digit, and now we are scanning the number from right to left, and we are grouping 3 bits at a time, and then we will write the corresponding octal equivalent. 001 means it is 1, 110 means it is 6, right? 110, again 110 means it is 6, again 100 means it is 4. So this is the octal equivalent. So finally for the given hexadecimal number 3p4, the corresponding octal equivalent is 1664. 1664. So this is one way of finding the octal equivalent for the given hexadecimal number. So there is one more procedure. This is simple procedure, but there is another procedure. In that way also we can solve. What is that means? For the given hexadecimal number, we have to convert, or we have to find the decimal equivalent, and then for this we have to find the corresponding octal. So this we will see in later classes. So till now whatever we have seen, so we have used that procedure, but in this way also we can convert. So we have to find for the given hexadecimal number, first we have to find the decimal equivalent, and then from the decimal number we have to find the corresponding octal equivalent. But this procedure you can follow. For the given hexadecimal number, first you find the binary equivalent, and then you convert that binary into octal equivalent, right? We'll see one more example so that it will get clarified further. So it is having both integer part as well as fractional part. So for the given hexadecimal number, we have to find the octal equivalent. So what we have said, so first convert the hexadecimal number into binary, and then convert the binary into octal equivalent. So right, for the given each hexadecimal equivalent, the corresponding binary equivalent. So for 1 it is 0, 0, 0, 10001. For 5 it is 01010101, and for 3 it is 0011. For D means 13, so that means 1101. Right? Now first we will write the binary equivalent. So 0010101. So this is the integer part. For fractional part I am writing here at the bottom 00111 and 1101. So this is the binary equivalent. Now we will group the numbers 3-bit at a time for integer part as well as fractional part separately, and then we will write the corresponding octal equivalent. So these 3 bits one group, so these 3 bits one group. So here we have only 2 0, so we will append 1 0, right? So these becomes one group. Next, for the fractional part we have to scan the number from left to right. So these 3 into 1 and these 3 into 1. So here we left with only 2 digits. So we'll append 0 at the trailing end. So this becomes another 3 group. Now write the corresponding octal equivalent. So for the first 3 bits anyway it is 0. So even if you don't write it is fine. Then 010 means 2. 010 means 2, and 101 means corresponding octal equivalent is 5, and then follows this equivalent at a point. Then 001 means it is 1, and then 11 means it is 7, and again 010 means 2. So this is the octal equivalent for the given hexadecimal number 15.3D. The corresponding octal equivalent is 25.172, right? So for integer part you have to write, and fractional part you have to write. First we have written the corresponding 4-bit binary equivalent, and then we have scanned for the integer part, we have scanned the number from right to left, whereas for the fractional part we have scanned the number from left to right, and we have written the corresponding octal equivalent for each 3-bit group, right? We'll see one more example. Hexadecimal to octal. So here also we have the integer part as well as the fractional part. So first we will write the binary equivalent for each hexadecimal digit. So 0, 1, 1, 1. For 6 it is, so these are, we are writing first the binary equivalent. For 6 it is 0, 1, 1, 0, and for 8 it is 1, 0, 0, 1, 0, 0. So first we will write the binary equivalent 0, 1, 1, and then 0, 1, 1, 0, and for fractional part we have 1, 0, 0, 1, 0, 0. So this is the binary equivalent. Now we will scan the number from the radix point. So these 3 bits into one group. So these 3 bits into one group, and here we left with 2 bits. So we will append 0 and we will write. So and similarly, so these 3 bits into one group, we can append 2 zeros. So these 3 into one group, and here also we can append 1 0, so that these 3 also will become one group. Now we will write the corresponding octal equivalent for each 3 bits. So 1, 0, 0, 1 means 1, 1, 1, 0 means 6, again 1, 1, 0 means 6, right? 1, 0, 0 means it is 4, this all zeros means 0. So for the given hexadecimal number, the corresponding octal equivalent is 166.40. 166.40. So for the given hexadecimal number 76.8, the corresponding octal equivalent is 166.40. Right? Is it clear? So what we are doing? Simply we are writing first we are converting the hexadecimal number into binary, and then we are converting from binary to octal. Right? Is it clear? Now we will see how to find the hexadecimal equivalent for the octal. So what we have to do? So first we have to find octal to binary, then from binary to hexadecimal. So just the other way, So first for each octal digit we have to write the 3-bit binary equivalent, and then we have to convert the given binary number to hexadecimal number. So the same procedure whatever we have done for finding the hexadecimal to octal, the same procedure we will follow for finding the octal to hexadecimal. So for each octal digit we will write the corresponding 3-bit binary equivalent, and then we will convert that binary number into hexadecimal. So for 7 means the corresponding binary equivalent is 111, right? And for 4 it is 100, and for 2 it is 010, right? For 1 it is 001, and for 3 it is 011, right? Now first we will write the binary equivalent 111, 100, 010. I am writing here, or I will write here. So 010, let me continue here, 001 and 011, right? Now scan the number from right to left. Scan the number from LSB to MSB. Now group 4 bits. Group 4 bits. So here we have only 3. So append one leading 0. Right? Now write the corresponding hexadecimal equivalent. Hexadecimal 011 means 7, 1000 means 8, right? 1 again 1000 means 8, 1011 means it is 11, 11 means B. So for the given octal number, the corresponding hexadecimal equivalent is 788B. 788B. So what we have done? So first we have written for each octal digit the corresponding binary equivalent, and then the binary number we have converted into hexadecimal by grouping 4 bits at a time. So as it is having only the integer part, we have scanned the number from right to left. Right? Is it clear? We'll see one more example so that you can better understand. Now this number is having both integer part as well as fractional part. So whatever it may be, even if it is having the fractional part also, it is not a problem. So first we will write the binary equivalent, and then we will convert we will find the corresponding hexadecimal equivalent. So 1 means the corresponding binary equivalent is 001. So this is the corresponding binary equivalent. For 2 it is 010, and 3 it is 011, 4 means it is 100, right? Now write the number 0, 0, 1, 0, 1, 0, 0, 11, and then 100. So this is having both integer part as well as fractional part. So put the radix point appropriately. So 001, 010, 011 and 100. So scan the number for the integer part from right to left, For fractional part, scan the number from left to right. So we have to find the hexadecimal. So we have to group 4 bits at a time. 4 bits at a time. 4 bits at a time. So here we are left with only 2 zeros. So we can append 0. So that doesn't matter. So the corresponding hexadecimal equivalent is 0. So this is 1010. 1010 means A, and this is 0111 means 7. So put the radix point 7, and again these are all zeros. So 0. So for the given octal number 12.34, the corresponding hexadecimal equivalent is A7. The corresponding hexadecimal equivalent is A.7. A.7. So what we have done? We have first found the 3-bit binary equivalent for each octal number. Then we have found by grouping each 4-bit the corresponding hexadecimal equivalent. So this is the procedure. Now we will do one more example. So for 3, first we will write the corresponding 3-bit binary equivalent 0 1 1 0 1 1. For 5 it is 1 0 1. For 4 it is 1 0 0. 6 means it is 1 1 0. Now write the number. 3 means 0 1 1. 5 means 1 0 1, and put the radix point. 4 means 1 0 0. 6 means 1 1 0. Now this, for the integer part, scan the number from right to left, group 4 bits at a time. So here we left with only 2 bits, so we have to append zeros. For the fractional part, scan the number from left to right and scan and group 4 bits at a time. So here also we left with 2 zeros, so we have to append 0. So if we append zeros to 0 0 0 0 1, the corresponding hexadecimal equivalent is 1, and then we have 1 1 0 1. So this means 110 means 13. 13 means it is D. Again 1001 means 1001. The corresponding hexadecimal equivalent is 9, and we have 1 0. So for this we have to append 2 more 0. 1 000. The corresponding hexadecimal equivalent is 8. So for the given octal number 35.46, the corresponding hexadecimal equivalent is 1B.98. So this is the corresponding hexadecimal equivalent for this given octal number, right? So here I will stop. So in the next lecture, we will see radix r, whatever may be the base that is given, whatever may be the number system, how to find the corresponding decimal equivalent for this. And again, some decimal number is given to us, how to find the any radix or any, how to convert to any number system. So that we will see in the next lecture. So in this lecture we have seen the hexadecimal number system and how to find the conversion from octal to hexadecimal and hexadecimal to binary, binary to hexadecimal, and hexadecimal to octal. Thank you for watching. I request everyone to subscribe our Easy BTech channel and share to your friends. Thank you.